The first part of the FRQ, we just need to take the derivative implicitly and solve for dy dx and make sure it matches that right there. So if we take our function up here, take the derivative right across, derivative of 2x squared is 4x, plus derivative of 3y squared is 6y, dy dx. I always take out the negative sign here and just take the derivative of 4xy and deal with the negative sign later and distribute it, up to you guys. Otherwise I end up kind of screwing up my negatives. So we have derivative of, let's make this our first part, so we have 4x and y. Derivative of 4x is 4 times y, plus the derivative of y, which is dy dx, times 4x, equals derivative of 36, which is 0. So we end up with 4x plus 6y dy dx minus 4y, I'm distributing the minus sign, subtraction sign, minus 4x dy dx equals 0. Now let's keep all of the dy dx's on this side. So if we pull out the dy dx, we have dy dx times 6y minus 4x, oops, that's not a 6, or that's not a 4, that's a 6, equals, and then if I add 4y to the right and subtract 4x from the right, or get rid of it on the left, here's what we have. And then if we solve for dy dx, we end up with 4y minus 4x over 6y minus 4x. And if we were simply taking the derivative, we could leave it, but we need to show that it equals this right up there, and we can get there if we divide top and bottom by 2, which we can do because we're doing the same thing to the numerator and the denominator, so it doesn't break any laws of math. So dividing the top by 2, 2y minus 2x, divided by bottom by 2 is 3y minus 2x. And there we go. It matches this, which was pretty much the point of the problem. Actually, literally the point of the problem. Part B, we want to find the slope of the line tangent to the curve at each point on the curve where x equals 6. Okay, so we know that dy dx equals 2y minus 2x over 3y minus 2x, which we did in the previous problem. And looking at this, to find the slope, we need an x and a y. So we have an x, so we're looking for what our y will be. So then we go back to our original equation. So if x is 6, we have 2 times 6 squared plus 3y squared minus 4 times 6 times y equals 36. 6 squared is 36, 2 times 36 is 72, plus 3y squared minus 4 times 6 is 24 times y equals 36. So we end up with, if we move everything over to the left, we end up with 3y squared minus 24y. Subtracting 36 from both sides, we end up with plus 36. This is equal to 0, so by the zero product property, we can find the solutions or the zeros. We take out a 2. 3 times y squared minus 8y plus 12 equals 0. We can conveniently factor that into y minus 6, and y minus 2 is 0. So our y values are 6 and 2. So now we end up with 2 points to work with and to find our slope of our tangent line. So we have the point 6, 6 for when y is 6, and we have the point 6, 2 for when y is 2. And then we'll go back to our derivative which was dy dx equals 2y minus 2x. I'll rewrite it here just so we have it. 2y minus 2x over 3y minus 2x. And if we put in the 0.66, y dx equals 2 times 6 minus 2 times 6 over 3 times 6 minus 2 times 6. 12 minus 12 on the top is 0, divided by 18 minus 12, which is 6. So the slope of the tangent line at the point 66 is 0. For the point 62, dy dx will be 2 times 2 minus 2 times 6 over 3 times 2 minus 2 times 6. The numerator is 4 minus 12, which is negative 8. The denominator is 6 minus 12, which is negative 6. So the slope of the tangent line at the point 62 is 4/3. So these are both of the derivatives or slopes of the tangent lines when x equals 6. Part C, we want to find the positive value of x at which the curve has a vertical tangent line, and we have to show our work. Once again, we know our derivative or slope of the tangent line, dy dx equals 2y minus 2x over 3y minus 2x. And so now what we're looking for, vertical tangent line, means we have an undefined slope. And since we have a fraction, to make it undefined, that means our denominator will equal 0. If we wanted a horizontal tangent line, the slope would be 0 rather than undefined, and then our numerator would be 0. So let's take our denominator, 3y minus 2x, and set it equal to 0. And so let's solve for y. You could solve for x if you wanted to, just solving for y, because that's what seems to make sense to me. If we divide by 3, we know that y equals 2/3 x. And you might be thinking, great, what good does this do us? Well, now we can go back to our original curve and substitute 2/3 x for y, and then we have a single variable. So let's do that. So we have 2x squared plus 3 times 2/3 x squared minus 4x times 2/3 x equals 36. So 2x squared plus, well, 2/3 x squared. Well, we can just show the step versus doing it all in my head. You can skip steps wherever you want. So we end up with 3. This part squared is 4/9 x squared minus, this ends up being 8/3 x squared equals 36. We'll keep simplifying. 2x squared plus, this right here turns into 12 over 9, which is the same as 4/3 x squared minus 8/3 x squared equals 36. So now let's see, we have 2, which is 8/3, not 8/3, 2, which is 6/3, plus 4/3, which is 10/3, minus 8/3, which is 2/3 x squared equals 36. Almost there. You can divide by 2/3. I tend to look at it as multiplying by 3/2. Makes more sense in my head. So we end up with x squared equals 36 times 3 halves. Well, 36 times 3, I'm sure I could figure it out, but I know 36 divided by 2 is 18, and 18 times 3 is 54. Square root both sides. X is positive and negative square root of 54. So now I've done a bunch of math and I forgot what I'm actually finding. We were looking for the positive value at x at which the curve has a vertical tangent line. So we don't want the negative square root of 54. So our answer is just x equals square root of 54. And we are all set.